In exercise 12.10, we're continuing with some multi-step synthesis exercises. And one trick that we've noticed already is to count the number of carbons at the beginning and at the end of your synthesis. So on the left we have 5, and on the right we have 1, 2, 3, 4, 5, 6, 7, 8. Right, so 1, 2, 3, 4, 5, 6, 7, 8. 8 carbons there. So we're adding 3 carbons. We're adding 6, 7, and 8. 1 through 5 have been there from the beginning. And the reason why that's a useful thing to check in the beginning of a synthesis is because there's only one way to add carbons, so it really narrows down what you have to think about. The only way to add carbons is using a terminal, that we've learned in this semester, is using a terminal alkyne, and that's exactly what we have. If you have a terminal alkyne, an alkyne at the end of a carbon chain, one of the carbons in the triple bond will be bonded to a hydrogen, and that hydrogen is a little acidic. So all you have to do is treat that with a strong base like sodium amide. The amide here is the really reactive part. It has 2 lone pairs, a full negative charge, and that rips this hydrogen off. The electrons snap back into the sp orbital of that carbon in the triple bond. So what we end up with after that first step is, crucially, a carbon nucleophile. Now, it doesn't look like that's a big change, but it really is, because this carbon nucleophile can now participate in SN2 reactions. So we can sort of take the part of this molecule that we want to add on, those carbons 6, 7, and 8, we can take those, and instead of being bonded to carbon number 5, we can have them bonded to a leaving group, so like a bromine. So we have carbons 6, 7, and 8, and where we want this nucleophile to attack, we just put a leaving group on it. That gives us an alkyl halide that we can use. We can use it because the nucleophile can now swoop in here, attack the slightly positive carbon there, and kick the leaving group off. So that's a classic SN2 reaction. We have nucleophilic attack and loss of a leaving group happening at the same time. Okay, so at that step, after that step, we now have all 8 of our carbons. So we would have our original carbon chain with the 5 carbons. And then attached to it, instead of the bromine, where the bromine was, we'll have a triple bond. So I'm going to draw this first, it'll look a little strange. I'm going to draw this first like this. Here we go. So that's our molecule. That's what we have at this point. Okay, let's take stock. Let's compare what we have to what we want. We have 1, 2, 3, 4, 5, 6, 7, 8 carbons. That's great. With a triple bond between carbons 4 and 5. What we want is 8 carbons just like that, but with a double bond between carbons 4 and 5. And specifically, we want a cis double bond. If you draw a line down the long end of the double bond there, and then you compare the direction that the 2 carbon chains are going in, you'll notice they're going in the same direction, right? They're not crossing that line. They're both going down relative to that line. So they're on the same side of the line of the double bond. That makes them cis. So we want a cis alkene, and we only know one way to make a cis alkene. We can take this triple bond and treat it with, we can bubble hydrogen gas through it and sprinkle in some of Lindlar's catalyst. And that'll do it. That'll turn this alkyne into our alkene. So it will turn that alkyne with the triple bond between carbon 4 and 5 into this cis alkene with a cis double bond between carbon 4 and 5. So the main thing here, a big principle we saw, is how to make a new carbon-to-carbon bond. right? We compared the number of carbons in the reactants and the products, and we saw that they increased. The only way we know how to do that is with sodium amide, a terminal alkyne treated with sodium amide, to turn it into a nucleophile, and then treat that with an alkyl halide to do an SN2 reaction, and that creates a new carbon-to-carbon bond. Once we had that new carbon-to-carbon bond, we can play with the electrons in the triple bond, and here we were able to turn them into a cis alkene. All right, let's try B. Well, that procedure worked so well for us last time. Let's try it again. We've got 1, 2, 3, 4, 5 carbons on the left. We have 1, 2, 3, 4, 5, 6, 7 carbons on the right, so we're adding 2 carbons. Now, it might be tempted, and so we know anytime you add 2 carbons, you want to use a terminal alkyne, treat it with sodium amide, and react it with an alkyl halide. Now, we have here, it might be tempting to look at this and say, well, that's a terminal alkyne. Let's use that. Let's rip the hydrogen off of that. And I'll just do this quickly because it's a misleading line of thought. If you rip the hydrogen off of that with sodium amide, and you create a lone pair there with a full negative charge, and you'd say, okay, well, I've got 1, 2, 3, 4, 5 carbons. I just need the 6 and the 7. So let me add 2 more carbons with a leaving group on them so that I can do an SN2 reaction. The problem with this is that after you make that, there's no way we can control the placement of the electrons, right? Even if you make that, and this has the right number of carbons, it has 7 carbons, but what's wrong with it is that the pi bond is in the wrong place. The pi bonds are in the wrong place, the triple bond, the alkyne. And we've learned a way to walk electrons across a molecule, but in order to do that, we have to do Markovnikov or anti-Markovnikov addition, and then either get the Hofmann or the Zaitsev base through elimination, or a product through elimination. But in order for that to happen, there has to be a difference between the 2 bonds in the triple bond, the 2 carbons in the triple bond. One has to be more substituted than the other, and then we can control the direction that the electrons go in. But here, both of these carbons, carbons 4 and 5, are equally substituted. Carbon 5 is bonded to 2 other carbons, so it's secondary. Carbon 4 is bonded to 2 other carbons, so it's secondary. So we can't control where things will add on that bond. And so it's not especially useful. We can't reliably and in good yield walk the electrons toward the right end of the molecule. So although this is very tempting, it is misleading. We had the right reaction, we just didn't have the right terminal alkyne. Well, we know that we need two things in order to do this reaction. We need a terminal alkyne and we need an alkyl halide. If this isn't useful as a terminal alkyne, maybe we can turn it into an alkyl halide and bring in a separate molecule as the terminal alkyne. So this is carbons 1 through 5. What if we turn this into an alkyl halide, turn carbon 5 into an alkane that has a bromine on it, and then we just bring in ethyne or acetylene as a separate nucleophile, right? So if we take ethyne or acetylene and we treat it with, we know there's a hydrogen here, a hydrogen on both sides of here. If we treat that with 1 equivalent of sodium amide, it'll rip one of those hydrogens off and turn that molecule into a nucleophile. Well, actually, and all that would need is a leaving group on carbon number 5 to attack. Okay, so how can we turn this into an alkyl halide? Well, it might be tempting to just add HBr. Like if you add HBr on here, then, you'll have a bromine. But there are a couple problems with that. First, we have to worry about the placement of HBr. We want to make sure that the bromine is on carbon number 5, because that's the carbon that we want our nucleophile to attack. And so because 5 is less substituted, 5 is a primary carbon and 4 is a secondary carbon, we would want the hydrogen to go to the more substituted carbon. That would be anti-Markovnikov addition. And so you'd have to use peroxides. That's the first thing. But the second thing is, if we use one equivalent, if we just try doing that with one equivalent, then we'll have 1, 2, 3, 4, 5. We'll still have one pi bond. And the hydrogen and the bromine will be on there, sure. But what we want is an alkyl halide with all single bonds. And we could hydrogenate that. You could just bubble H2 gas with platinum, palladium, or nickel, and that would give us our product. That would give us something that would be useful, an alkyl halide. So that's one possibility. Or you could sort of do it in reverse. You could do the hydrogenation first. So you can hydrogenate it either with Lindlar's catalyst or with sodium in liquid ammonia. Both of these take an alkyne to an alkene. Lindlar's catalyst would take it to a cis-alkene. Dissolving metal reduction would take it to a trans-alkene. Here, this can't be either cis or trans because it's terminal. And so you could use either one. Either way, you would get an alkene there. And then you could do the HBr with peroxides to get the anti-Markovnikov product. So the hydrogen would add to the more substituted carbon, and the bromine would add to the less substituted carbon. We'd end up with this same thing. Now, this might seem unnecessarily complicated, the fact that I wrote 2 separate pathways out for this. But I did this to illustrate an important thing to remember about synthesis exercises. There is almost always more than one way to accomplish a transformation. So in these videos, I often will just give you one way, but there may be others. If you think you have another, send it to me, check with me. I'd love to see your work on how you try to connect the dots and give you feedback for it. It's part of what's so fun about these is that there's such an opportunity for creativity. It's not just a linear, rote, robotic process, but it's a creative and a critical thinking type of process. Well, either way we do this, the purple or the green, we end up with this alkyl halide, and that's what we wanted, right? We tried using this as the terminal alkyne. It didn't work, so we're going to try to use this molecule as the alkyl halide. So we'll take our alkyl halide, we'll react it with the nucleophile that we made above. So above, we made this carbon nucleophile by adding sodium amide, and then that would do the SN2 reaction. So this would attack there, kick the leaving group off, and we would have these 1, 2, 3, 4, 5 carbons attached to the carbons 6 and 7. So we would have this molecule without the bromine would have left, and then it's going to attach to carbon number 6, the nucleophile of this ethine. So we form this new bond here. Oops. And that is the product that we wanted. up here. Okay, so let's review our thinking for this exercise. We counted the number of carbons. The one on the left had 5, the structure on the right had 7. We saw that the number of carbons increased. That meant there's only one way we know how to do that, how to increase the number of carbons in a molecule so far in Organic Chemistry 1. And that is using a terminal alkyne. We saw that we had a terminal alkyne to begin with, and so we tried to use that, but we ran into trouble because when we did that and treated that with an alkyl halide, the terminal alkyne, or the alkyne, got stuck in the middle of the molecule, and we didn't have a way to walk it to the end because both carbons in the alkyne were secondary, so we couldn't use a Markovnikov or anti-Markovnikov addition to control where the direction that we're moving electron and reactivity in, electrons and reactivity in. So using this terminal alkyne didn't work, so instead we flipped our thinking around. We know that to add new carbons, we have to have a terminal alkyne and an alkyl halide. If this doesn't work as the terminal alkyne, maybe it will work as the alkyl halide. So we turned it into an alkyl halide, and we saw that there were 2 ways to do that. We could do that by first adding one equivalent. This is this purple one. First adding one equivalent of HBr, and because we wanted the bromine on the end and the hydrogen on the more substituted carbon, we added peroxides to get the anti-Markovnikov product, and then you can hydrogenate that. Or you could do it in the reverse way. First hydrogenate it, but so that you get an alkene. H2 in Lindlar's catalyst would give you cis, dissolving metal reduction would give you trans. This can't be either, so it doesn't matter which one you use. And then you do the anti-Markovnikov hydrohalogenation, HBr in the presence of peroxides. Either way, you get your alkyl halide, your 5 carbons with a leaving group on carbon number 5. We just had to add these last 2 to create those. We just take ethyne, use one equivalent of sodium amide to turn it into a nucleophile. Then we can react that with the molecule we had. You get the SN2 reaction, and that's your product. So overall, if you were just going to write this recipe down for a chef who wanted to go through this, I'm just going to write one of these. What you would do is, let me write the purple one. First thing, you'd use one equivalent of HBr and peroxides, in the presence of peroxides. And then you'd follow that up by bubbling some hydrogen gas through a solution that has either platinum, palladium, or nickel catalyst. You wouldn't have all 3 of those, just one of those metal catalysts. That would give you this product right here. Then you'd want to make your carbon nucleophile by taking ethyne and reacting it with sodium amide, one equivalent, so that it just rips one of these hydrogens off. That allows you to do this SN2 reaction, and oftentimes if you add this strong base here, it could try to steal that hydrogen off, so just to be safe, it's often a good idea after you use sodium amide to do a water wash. And those steps would be one plausible synthesis for accomplishing this transformation. Notice if you could also write down the steps for the green pathway, but just for the sake of time, because we already walked through that, I won't write those all out. Okay, let's try C. Well, we can play the same game. How many carbons here? We have this 6-membered ring, the cyclohexane. That doesn't change. You have a methyl group on it. That doesn't change. On the other branch, we have 1, 2 carbons, and here we only have 1. We have fewer carbons on the right than we do on the left. Well, there's only one way that we've learned to remove carbons from a carbon chain, and that was ozonolysis. Now notice here what you have is not an aldehyde or a ketone, but a carboxylic acid, a carbon double bonded to oxygen with an OH on one side. We only learned one way to make those. That was by doing ozonolysis specifically from an alkyne. So we could make that. Notice how we're sort of thinking backwards. We see a feature in the product that's a sort of a key feature, and we said, okay, well, we can make that if we had an alkyne there. If, instead of the double bond to the oxygen, we had a triple bond Oops. We had a triple bond between two carbons. So if we had that, and you do an ozonolysis on an alkyne, and the recipe for that is always ozone in the first step. For an alkyne, it's H2O in the second step. Compare that with an alkene. If you do ozonolysis on an alkene, it's ozone followed by DMS. So for an alkyne, you use water in the second step. That would saw this in half, remove this carbon on the end. That would bubble away as carbon dioxide. And the other carbon here, this one carbon there, would turn into the carboxylic acid. The oxygen's coming from the ozone. So if we had this alkyne, we could do ozonolysis and get this carboxylic acid. But how can we get the alkyne? What do we have to work with? We have two bromines. And the bromines, and if you notice, if you number these, you have 1, 2, that's like 1, 2 here. You see the bromines and you should think, oh, those are leaving groups. I have two leaving groups. That means I can do two elimination reactions. Each elimination reaction will create one of the pi bonds. So one elimination creates one pi bond, the other elimination creates the other pi bond. To do two elimination reactions in one step, it's a two-step procedure. You add excess sodium amide, and that rips these off. It creates the terminal alkyne, actually, all by itself. But in addition to that, it rips the hydrogen off here. There's a hydrogen on this terminal carbon. It rips that off and it turns that carbon into a nucleophile, which is unstable, so you don't want that. You have to stabilize it, and so in a second step, you shake it up with some water, and then you do this basically steals a hydrogen from the water, does a proton transfer to turn back into its stable self. So that will turn this original molecule into the alkyne, and then once you do ozonolysis on the alkyne, you will get rid of this one carbon, and you'll be left with a carboxylic acid. So that overall, you'd have 4 steps for the synthesis. First, you'd treat it with excess sodium amide, followed by water. That will turn this vicinal dihalide, you have 2 halogens on neighboring carbons, vicinal dihalide, into this alkyne. And then you can get rid of one of those carbons. You can saw it off the molecule by doing ozonolysis. So that always involves ozone in the first step. Because you're doing it on an alkyne, you have water in the second step. And so that recipe would accomplish that transformation. Okay, let's look at D. Now in D, if you count the number of carbons, we've got 1, 2, 3, 4. Here we have 1, 2, 3, 4, 5, 6, 7. We have more carbons. Well, we only know one way to add carbons. That's using a terminal alkyne and sodium amide to turn it into a nucleophile and then an alkyl halide. Well, we don't have a terminal alkyne, we have a terminal alkene. But we have learned already a trick. We can turn an alkene into an alkyne. It's a 2-step procedure. Well, I guess 3 steps if you include the water wash. The first step is to add Br2. So we've seen this in a previous video and walked through it step by step, so I'm just going to quickly go over it here. The first step is to add Br2. That will add a bromine onto each of those carbons in the double bond. Now you have 2 leaving groups, and you can do elimination twice. Just like we saw in the previous exercise, that means you can use sodium amide, an excess of it, that will accomplish both of the eliminations, but leave you with a carbon. Well, let me draw it out. So after you have the sodium amide, you would eliminate both of those, create 2 pi bonds, and here I'll just redraw this because it's really a linear molecule, so I'll just move that around. So that's what we would have, but then the sodium amide, there's a hydrogen here, the sodium amide would steal that and the electrons would snap back onto the carbon, and that would be an unstable carbon nucleophile. So we do a water wash, and the negative charge here steals one of the slightly positive hydrogens from water. You do a proton transfer, and that stabilizes it. So so it puts a hydrogen back there. Now, I'm going to erase that. That hydrogen is still there. It's just implied in this skeletal structure. Well, now we have our terminal alkyne. And actually, we can treat it, ironically, with more sodium amide. So maybe this water step isn't necessary after all, but just for consistency, I'm going to keep it there. If we treat it with sodium amide again, it will rip that terminal hydrogen off, and we'll get the nucleophile there. Now, what's special about that nucleophile on carbon number 4 is it will allow us to create a new bond to another carbon. So we're going to take carbons 5, 6, and 7, and what we can do is have it as an alkyl halide. So if we have an alkyl halide on carbon number 5, we can do an SN2 reaction, and we would attach this carbon chain to this carbon chain. So we'd have those 3 carbons there attaching. Now we do have a new bond between carbons 4 and 5, and we have the right number of carbons total, 7 carbons. But if you look at this, you'll see a problem, and it's a similar problem as we've seen in a previous exercise in this video. We have an alkyne, and both of the carbons in it are equally substituted. They're both secondary. We want to walk the reactivity in this molecule from being between carbons 3 and 4 to being between carbons 5 and 6. But because these are the same substitution, we can't use our tricks of Markovnikov or anti-Markovnikov addition, using a skinny base or a bulky base. We can't use those tricks to walk the electrons over because these carbons are equally substituted. So there is no such thing as Markovnikov or anti-Markovnikov addition with this, because there is no less substituted carbon. And so we're at an impasse. We can't get from this to the products. And this is another useful, even though this reaction this procedure didn't end up working out, I wanted to work it out this way to illustrate another important feature of solving synthesis problems. That is to always try things and not to be afraid of them not working out. It happens. It's a natural process of doing these synthesis exercises. If a synthesis that you design doesn't work out, that still gives you information. For example, here, we knew that we had to do this general reaction. We knew that we had to have a terminal alkyne attack an alkyl halide. That's the only way that we know to add carbons. But what should be the terminal alkyne? What should be the alkyl halide? Well, we tried something. We tried making this the terminal alkyne. That didn't work. So we switch our thinking around. The fact that didn't work gives us information. We know that this is not the terminal alkyne anymore. That means it has to be the alkyl halide. So that's a valuable thing to learn, and that's how science works in general. In science, when you're doing experiments and trying to get information, it doesn't matter whether you get what you expected or not in the experiment. No matter what happens, you have new information, and that leads to better experiments. So you try stuff in science, and whether it works out or not, you get new knowledge, and that's a success. Now in this case, we know this has to be the alkyl halide because it won't work as a terminal alkyne. So we really want to turn it into this molecule here, where we have a halogen on carbon number 4, a leaving group there, because we want the nucleophile to attack carbon 4 so that we form this new bond here. Now we can do that. We can add, and notice we added not only a bromine but also a hydrogen here. This has only 1 hydrogen on it. This has 2, so we added a hydrogen. So this is hydrohalogenation, HBr. Notice that the hydrogen went on the more substituted carbon. Oops. The bromine went on the less substituted carbon. This one is secondary. This one is primary. So if the hydrogen went on the more substituted carbon and the halogen went on the less substituted carbon, that's anti-Markovnikov addition. Oops. Anti-Markovnikov addition. So to get anti-Markovnikov addition, we have to add peroxides in with that HBr. So that gives us our alkyl halide. Now next, let's think about what we want to add. We want to add this group right here, carbons 5, 6, and 7. So 3 carbons, but it needs to have a terminal alkyne. So we'll have 5, 6, and 7. 3 carbons. Now if we take those 3 carbons and we treat that molecule with 1-propyne, this molecule, with sodium amide, it will rip the hydrogen off the end there, and it will turn this into a carbon nucleophile. So this gets a lone pair and a full negative charge, and now you can do the SN2 reaction. This can attack carbon 4, kick the bromine off. And notice the beauty of this is that the reactive part of our molecule is in the right place. It's between carbon 4 and 5. So where the bromine was, now we have this nucleophile that displaced it. And notice we have the reactive part of our molecule between carbons 5 and 6. Oops, sorry, 5 and 6. Now the only thing is, here we have a triple bond, and what we want is a double bond. So we have to do some sort of a reduction. We have to add hydrogen somehow. If you notice, if you draw a line through the long end of this double bond, and you think about what direction the carbons are coming off of that, they're in opposite directions of that line. So that's a sign that this is trans. Or, if you prefer, E, if you remember in the EZ naming. Now, because it's trans, we know only one way to turn an alkyne into a transalkene. That's dissolving metal reduction, so you'd add sodium and liquid ammonia. Okay, so let's review this synthesis, what we did here. We added HBr in peroxides to get the anti-Markovnikov product, so the leaving group is on carbon number 4. And then we look at how many carbons we wanted to add. It was 3, and make that the terminal alkyne. You have to start with the alkyne and treat it with sodium amide, but then it's there. You wouldn't be able to store this product. You have to make that in the laboratory because it's so reactive. So you have to show that being made. Then you can do the SN2 reaction, gives you the alkyne with the reactive part of the molecule in the right place. You just have to turn the triple bond into a double bond, a transalkene, and you do that with dissolving metal reduction. So overall, if someone asked you how to make that transformation, you'd write down this recipe for them. First, add HBr in the presence of peroxides. Second, so that'll give you this alkyl halide. Second, take this alkyne, 1-propyne, and treat it with sodium amide. That'll make a nucleophile out of that. That will do an SN2 reaction. It'll give you this product. Finally, do a dissolving metal reduction to turn, so solid sodium and liquid ammonia, and that will turn that alkyne into a transalkene. So this recipe would accomplish that transformation. All right, let's try E. And we've got, let's try E. Actually, I'm going to do E and F in a separate video just to avoid making these videos too long.